Here we want to take a look at regular Markov chains and their significance in dealing with the transition matrix. This problem we did in the last section. Here's our initial state matrix. This is the transition matrix for this problem. We found the first state matrix by multiplying the two, and we can find the second state matrix by multiplying the initial state matrix times the square of the transition matrix. And we can find any future ones the same way. In fact, that's what we're going to do. What about over a long period of time? These are the ones that we just did. If we continued on, the third state, fourth state, fifth state, sixth state, seventh state, and so on, what sort of trend would we see? Well, let's take a look at it. These are the ones that we just computed. If we did the third state, and again all of these are typed on the calculator, and the fourth state, and the fifth, sixth, seventh, you notice any trends in the numbers? Here's the eighth, and we'll stop there and notice that the 0.75 is what all of these numbers are getting closer to. In fact, you'll see if you do this on your calculator that you could continue doing, just changing the powers of the p, larger and larger states. And 75% is going to be where it stabilizes. This is called the stationary matrix. Stationary matrix means that S times any value of P is going to give us the stationary matrix. S times P would be equal to S. A regular Markov chain always has a stationary matrix. So it's nice if we have a regular Markov chain. We can determine if it's regular if some power of the transition matrix has only positive entries. Here is an example. There is a transition matrix. Notice that every number in it is positive. That is the sure sign of a regular Markov chain. Here's another one. Is it regular? Well, not if there's a number in it that is not positive. However, it says if some power is positive. Let's do the second power of this matrix. Notice the second power comes out to have all positive entries. So this is a regular Markov chain. Look at this. If we want to find the stationary matrix, we need to solve the equation S times P equals S. We're going to make up a matrix for S and just use generic entries. We could have used A's and B's or X's and Y's or something like that, but these are the variables that we're trying to solve for. And so let's create an equation that says S times P equals S. And let's manipulate this. First off, we got to do the actual matrix multiplication. This is tricky. I'll show you how to do this on your calculator shortly. But look at this. If we take the row and the column and put them together using the properties of matrix multiplication, 0.7 times S1 plus 0.2 times S2, and that's got to equal to the first number in this matrix. And likewise, first row times second column gives this equation, and then we use the observation that we have to have the sum of S1 and S2 equal to 1. You've got to add up to 100%. If we solve this system of equations, we can use the addition method, substitution method, the Gauss-Jordan method. I'll show you how to do this on the Gauss-Jordan method. Here is the system of equations changed into the format for the Gauss-Jordan method. Here's the augmented matrix. If we do the reduced row echelon form of this, we come out with this. Notice the 1, 0.4 and 1.6 tells us that S1 is 0.4 and S2 is 0.6. That is our stationary matrix. That's a pretty good bit of work. There is a different way of coming up with a stationary matrix. Since we have a calculator that does these computations very rapidly, we can simulate this by taking our calculator, typing in the matrix, and doing various powers until we get a stationary matrix. The word stationary means it's not changing. And so the stationary matrix for this comes out to be the 0.25 and 0.75. In the long run, if we start off with this transition matrix, this is what we're going to end up with. 0.25 or 25% market share for the first object, 75% for the second.